Gomer from Louisiana State University, and I thank you all for leaving the sun, the food, and the drink for a few moments to join us for one of our later sessions of the day. As you know, our next session is called Toolkits, How to Make It, and we'll be having 4 papers, 3 long and 1 short. Our first paper will be presented by Ansh Verma, and he has 3 colleagues as well from Purdue University and Indiana University Bloomington. The title of the first talk, HandiMate, Create and Animate Using Everyday Objects as Material. Ansh?
Good afternoon, everybody. My name is Ansh Verma. I'm a master's student at C Design Lab at Purdue University School of Mechanical Engineering. Today I'm going to talk about HandiMate. It's a systems paper which was authored by Jasjeet Singh Seehra, co-authored by me, Dr. Kylie Peppler from Indiana University Bloomington, and Dr. Karthik Ramani from Purdue University. So essentially, what is HandiMate? And to answer that question, I have a small demo for you. Wait, there's more. So I guess by now you might have figured it out that it's a robotic toolkit with 3 basic attributes. First being a modular toolkit. So what I mean by modular toolkit is each of these, the robot which you saw right now was constructed of these 8 modules which we have. And the second attribute is crafting. So essentially what we have enabled in this kit is the act of crafting and constructing these robots and toys by mat board, cardboard, velcro, and sticking all together to these modules. And the third attribute of this kit is the gesture control. As you saw, I control this particular robot via my glove-based controller. So when we started designing this toolkit for everybody, we had certain design goals which we jotted it down, and we wanted to achieve those design goals. I'm going to discuss a little bit about those. So the first one being accessible. We did not want to confine the users with the specific predefined, pre-manufactured blocks on which they can build a robot. Rather, we wanted to give them the freedom of using everyday material or craft material or whatever they wanted to use to construct their toys. It should be easy to use. The kit should not have an extensive or a complex manual the user has to go through. Rather, the kit should be intuitive, and so that the robot which the user is trying to create should be easy to use, and it should be intuitive in a nature so that the user does not have to refer to a bunch of rules and a bunch of set of regulations to actually do this. It should be safe and robust. So the kit is designed for children as well as really old people, and we wanted to make sure the packaging is compact enough so that there is no hazardous action which can lead to some kind of accidents. It should have adequate and smooth movements. Basically, each reaction from the glove, each reaction from the user should be instantiated in a much more smoother fashion into the robot, based on which we thought that, okay, fine, we should have a very smooth movement robot. Essentially, this is a kit, so there should be a scope of improvement, which may also lead to improvement in the kit in technical terms like sensory modules or actuation modules, or scalability in terms of the users, where he can have multiple people playing in, or he can have multiple more modules on top of each other to build his toy. Lastly, it should be a medium of expression. So the robot, whatever the user is trying to create his robot, it should be a message, or it should enable the user to realize his imaginations and fantasies in a much more expressive manner. Keeping all these design goals in our mind, we came up with the system of HandiMate. So essentially, the system consists of 8 design modules. which are actuation-based, a glove-based controller, and a tablet interface. So what happens out here is the user, he creates this particular robot based on these 8 modules. The tablet interface is the interfacing medium between the user and the system, where the user informs the system of what he has created so that the system can recognize what gestures to map at what actions or what toys. So as I showed you, the biggest part of the kit are these small joint modules. They consist of electronics which contribute towards the communication system via an XP PAN network. It has a actuating system, actuation motor, which enables the rotary action of the module. On the sides of these side walls of the modules, we have provided velcro. So we are supporting the act of crafting and constructionism when the user can just push together or just statically, assemble his toy just by pressing together velcro from the static part to the dynamic part. Each module is capable of 2 types of rotation. First rotation being fixed angle rotation, where if you can look at this diagram, the upper body, if you consider the upper body as 0 position right now, it goes from -90 to +90 degree. And the second type of rotation is a complete 360 degree rotation, where the module rotates in a completely 360 degree manner. So based on all these modules, we came up with categories of toys which the user can create. The first one being vehicular toys, and the second one being non-vehicular toys. So vehicular toys can now further be classified as 2-wheeled and 4-wheeled robots, whereas the non-vehicular toys can further be classified as a robot, as a puppet, and the last category being an open-ended design. We also gave the freedom for the user to create non-vehicular toys on top of vehicular toys so that he can explore more innovative and complex design solutions. Please note that these vehicular toys and non-vehicular toys, except for the open-ended, have predefined gestures which we have designed. All this is possible via the tablet interface which the user uses to map the various gestures onto the system. Talking about the existing work, so there are commercial products like Lego Mindstorm and Easy Robot, which are available in the market. We have research work done. Topoboy is one of the very popular research work done. The way we differentiate from these existing kit is that we have a gesture-based controller where we saw an emergence of high level of engagement. At the second point, we are not using any pre-manufactured primitive blocks. Rather, we are using crafts and everyday objects and giving the freedom to the user to create and express in a more innovative manner. There, we feel that it will have a higher level of learning and higher level of expressivity. So the second talking about the second attribute, we have the glove. It's basically a wearable device which reads the hand posture of the user, and multiple of such hand postures when read are considered as a gesture. Now each dynamic gesture is then mapped on to associated action of whatever the user wants to create and whatever the user wants to associate to actuate the toy. Talking about the electronics, the glove has basically the way the glove reads the posture of the hand is via flex sensors and an IMU device. The flex sensors, there are 7 flex sensors which are laid on the fingers, joints of the fingers, the lower joint and the middle joint. There's an IMU device on the wrist which understands the orientation of the wrist. So collaboratively, they are able to inform the system of the particular hand pose of the user. We calibrated these flex sensors from a calibration exercise among the researchers, and came up with threshold value based on which the system would actuate or not. We also created a library of gestures where where we defined some very common gestures. For example, if you see in this video, the user shakes to start the system. He uses the flex sensors in the finger to give the fixed angle rotation, or he can use the orientation of his wrist via the IMU device to control the continuous rotation. And if he closes the fist, the system stops. So talking about the gestures. So as referring back to all the toy categories which I talked about earlier, we have developed this gesture library gesture library for specific toys. So first of all, the figure A represents a global gesture where the user, when created a toy, he can start the system by just shaking the hand as if he's trying to wake up the robot. And when he closes the fist, is as if he's terminating the command, and is the way the robot stops. The second category was puppet. So we consulted with a lot of puppeteers and considered her hand ergonomics to develop these gesture libraries. So what we essentially trickled down to was imitating a sock puppetry kind of an environment. We used these 3 fingers and instantiated shoulders, elbows, and neck, and we gave this as the predefined gesture library. Similarly, for a simple application called like robotic arm, we used the index finger and the lower 2 joints of the index finger and the orientation of the wrist as a 3 degree of freedom of a robotic arm. We also have regular toys where we tried to, replicated the action of acceleration and deceleration by the action of gas pedal. So imagine if you want to drive a vehicle, you would accelerate by pressing the pedal and decelerate by just releasing it. Similarly, if you want to turn left, you want to turn right. Based on the IMU values, we mapped all those predefined gestures to the system. Now we have the open-ended design open-ended design attribute of the kit, where the user can map whatever gestures what I've talked about to whatever actions he wishes to develop. This enables a complex system to be controlled by whatever gesture the user wants to do. Now the bigger question comes in, why did we do that? Why did we try to collaborate crafting? Why did we try to collaborate modular robotics and gesture control into a compact kit? The core essence of this exercise or this kit was crafting. So essentially what we wanted to do was enable the users to create these robots via the act of crafting. This crafting would enable them to give them a higher degree of design freedom. It would be highly expressive, and especially it will be a very known domain for them to construct these toys. So especially among children, they don't have to refer to manuals, or they don't have to refer to how to build up those toys. Rather, they have been doing all these actions. They have been crafting in the schools right from their childhood. So it's not very an alien technology to them. They just have to craft the toy and stick it together. This crafting enables a level of creativity and learning which we saw was high in this among our user studies. Talking purely from an engineering perspective, the user is able to create the robot right from scratch. So he has to create the primitives being the building blocks of these robots. He or she does not have to rely on predefined shapes. So there is a sense of engineering right from the very core, right from the very starting of this toy when he creates. This free-from primitive also enabled our higher iterative design process. So if he makes a tetrahedron, if he makes a cuboid, he sees that the system is failing or the robot is not able to take that load. So what he will do, he'll go back to his design book and recreate another primitive and maybe change the primitive orientations, maybe shift the blocks, maybe change the center of the, the weight distribution, make the structure more statically stable. So it's a highly iterative process. And this iterative process ended up with the user prototyping a dynamic structure. Now, please note that especially children who are not very aware of engineering terms, they were able to create toys which were highly engineering based. And I will talk about them. I'll complete these examples right now. So there were some very innovative engineering design solutions which you notice in our user study. For example, there was this teenager who created a very innovative steering mechanism. So if you see at figure B, the robot, a traditional four-wheel robot looks like this. And if he wants to maneuver the four-wheel robot, it would be not very smooth because of the differential. There's no differential action, and the turning radius, the front wheels will not turn accordingly. So what he actually did, he basically divided the chassis into two parts, and he connected both of the chassis using a glove, using one of our modules. Now he assigned a particular gesture to these modules, and based on these gestures, the modules, the front end of the car would turn in whatever direction he wants. So basically, he actually replicated a steering mechanism at his own level. And later he reinforced the structure with the velcro. We had another user who made a very interesting pulley-based crane, and he counterbalanced all the weights of the counterbalanced all the load via using heavy weights at the back. Interestingly, we also had a user who made this twisted quadraport, that's what he called it. And the interesting thing to note about this is that he controlled this entire robot by just one gesture. He mapped all the modules, all the actions of these modules just on the bend of the one finger. So he would just bend the finger, and the robot would enunciate, and he would perform this particular desired action of his. To qualitatively and quantitatively produce results of the system, we conducted a user study with 13 males and 6 females, out of which 12 were undergraduate students and 7 were school-going children. We had 2 settings of user study. The first setting being we would call the users into our lab, give them the materials, and give them 90 minutes to construct everything they wanted right from scratch. So they started with the design notebook, and they ended up with iterative prototypes. The second setting was we asked the student from the School of Arts, gave him a week to construct the toy, whatever he wanted, and wanted to see if we give HandiMate system to a guy for a longer run, how will he react. I'm very happy to let you guys know that it showcased a higher level of usability, and the users agree that it's easy to use, it's easy to configure with the tablet, and easy to control with the glove. So in summary, what was HandiMate? HandiMate was a robotic toolkit which enabled quicker prototyping, all the examples which I talked about were less than 90 minutes. It enables a highly iterative design cycle, especially by the act of crafting. It also supports learning by doing, especially for dynamic structures. And it leverages creativity and playfulness, especially among younger adults and children. And lastly, it encourages construction of big toys. So as you can see, the physical dimension of each of these modules is such that you end up making bigger toys. And we observed that they were exploring physics at a macro level, physics of macro structures. As an engineer, we could relate back to those. And teenagers at the age of 8 to 13, they were exploring all these toys. So we have a demo session. We have a demo session. Please stop by, and I'll be happy to welcome any questions if you have any. Thank you.
Okay, questions. I'll start off with the first question. Very nice work. It looked like many of your interactions were involving one person controlling one robot with a glove. I wonder if you've begun to explore one person controlling multiple robots or multiple people controlling one robot, 3 gloves, 5 gloves, 20 gloves, controlling a single bot. And if not, if you have any thoughts on the directions that sort of work might lead. Okay.
Yeah, thank you for the question. So, as I understand, there are 2 aspects of the question. The first aspect being one glove controlling multiple robots, and the second aspect being multiple gloves controlling multiple, or say, single robot. So the first aspect, we have done it. The user can control multiple robots using the same glove. It's just that he can create multiple robots and just use one glove to control this. We have not performed any studies which were specifically task-oriented to make multiple robots using the same glove, but yeah, we may plan to do that. Second part being a collaborative effort of using multiple gloves to control single robot. And we feel that this is one area which we would like to highly explore, and but yeah, we have not performed that, but we plan to do that.
Super. Do we have another question? Okay, then let's start transitioning, and I'll ask one more question.
Yep.
If you were to have 10 additional people on your team, 1 or 2 years to develop one or a family of flagship applications, really to sort of push the bounds of what this could be, do you have any thoughts on the directions you would be inclined to go?
Yeah, so I guess that's more like a... So I guess that has a more commercial aspect to it. Maybe, yeah. So purely in terms of research, what we are doing right now is technically extending the kit, maybe adding more actuators, maybe adding more sensory modules, and trying to see where the thing goes. But In terms of more applications, I feel that it's totally up to the users what they make. We just want to provide them the kit and give them the experience of interaction.
When someone pushes you and they say, for these $5 million, we need to show one example to really light their minds on fire, or two or three, some small family. Do you have a sense? Most promising direction, perhaps for many people with gloves controlling one larger structure? Or,
So what we also observed that they would relate very highly towards popular characters. So like, for example, Wall-E or Kermit. So if we can show some flagship robots, like Wall-E or Kermit, so maybe they will be attracted more, I guess. Yeah.
Thanks so much. Let's give another round of applause.